Good afternoon, honorable judges. My name is Yanshen Li.
My name is Yingwen Ho.
We are from Taiwan, Kaohsiung Girls Senior High School. It's our pleasure to introduce our research to you today, and our topic is the optical studies of calcium tartrate precipitation from water. In this study, we are talking about diamonds in the wine. When we taste wine with our family or friends, we often see that there are wine diamonds on the bottom of the bottle or on the cork. After doing some research, we know that the main composition is tartaric acid. And the tartaric acid mainly consists of potassium bitartrate and calcium tartrate. The formation of white diamonds are influenced by pH, temperature, seeding level, degree of supersaturation, and concentration in the related research. Therefore, we focus our projects on these factors. In order to give a comprehensive knowledge of tartaric acid, we will briefly introduce the chirality of tartaric acid. We know that the tartaric acid has three different optically active forms: meso, levorotatory, and dextrorotatory. Alphone and diphone compounds have good solubility in H2O, and they are optically active, so they are enantiomers. Because of the symmetrical forms, meso compounds are optically inactive. There are DL tartaric acid in 1:1 in racemic compounds. Thus, they are optically inactive too. The research is divided into two parts. In the first part, we took advantage of spectroscope and Tyndall effects, exploring the calcium tartrate precipitation process. In addition to the effect on different concentrations or pH values of calcium ions, we dug into the reaction between calcium ions and carbonates or hydroxide, which are optically inactive. In the second part, we made use of homemade polarimeter. It was not only monitored to see if it is usable or stable, but also the change of optical rotation values were observed when the calcium tartrates precipitated. Next, we are talking about the effect on calcium tartrate precipitation. Looking at the figure, we can know that the higher concentration of calcium ion will lead to the increase of precipitates. We can make use of spectroscope to observe the diffuse light. We try to adjust the concentration of calcium ion, preventing the diffuse light in the solution from affecting the results of the polarimeter. Because of it, we use the calcium ion in 0.02 m to do the later experiments. Then, we use the same way to observe the other optically inactive substances and make sure if they change optical rotation values or not. We use calcium carbonate and calcium hydroxide and saw that they have a clear Tyndall effect. However, they are optically inactive. They don't disturb our experiments. Finally, we can conclude that only the precipitation of calcium tartrates make optical activity change. Next, we are discussing about the calcium tartrates in different pH values. We know that the tartaric acid is diprotic acid. It has different forms and different pH values. When the pH is 2, the main composition in the solution is tartaric acid. When the pH is 4, the main composition is bitartrates. When the pH value is bigger than 7, the main composition is tartrates. We can see that when the pH is 4 and pH is 12, the solution has different optical sizes, particle sizes, and Tyndall effects.
For the experiment, we wanted to know the principle of polarimeter and offer a simple way for everyone to do some fun optical experiment. Therefore, we refer to the paper and make our homemade polarimeter. Our homemade polarimeter has 5 main parts: the light source, the polarizer, the sample cell, and the analyzer. Next is the detector with a voltmeter. We use a lighter as light source, and the polarizers came from the old cameras. We can see when the light goes through the polarizer, the light will change into the plane polarizer. The plane polarizer will be inflected by the compounds in the sample cell. And we operate the analyzer, which is done on a protractor, until the voltage reaches the highest number, and we can know the angle. Next, we wanted to know how our homemade polarimeter worked and difference between our homemade one and the one which is commercially available. So, we made an experiment to compare with homemade polarimeter and a commercial available one. According to the figure, we can see the homemade polarimeter has the same trend and result to a commercially available one. That makes us amazed about its good stability, so we decided to use it in our project. And this is our initial experiment to see if we remove the precipitate, will the solution become optically or not? By the figure, we can see the volume is almost 0, which means the things make the solution become optically active was removed. So we predict that there was some unknown compound formed, but it was removed as a precipitate. Next figure supported our guess. We can see the black line, which is tartaric acid, is optical inactive, and the blue line and purple line, that's those with a lot of precipitate that cover the light. However, the red line, which didn't form any precipitate, its optical rotation changed. Another thing we can see in this figure is, after about 30 minutes, all the volume back to 0. So we predict that there were some unknown tiny particles formed in the beginning, which is optical active. As time went by, the particle would be bigger and bigger. Finally, it would become a precipitate. After a precipitation, the volume back to 0 again. The next experiment, we are talking about the effect on different pH volume. According to a dissociation diagram, we can see when pH is 2, the main composition is biproponic acid, which is tartaric acid in our experiment. When pH is 4, the main composition is monodentate, which form calcium D bitartrate in our experiment. When pH is 7, the main composition is bidentate, which formed calcium L tartrate in our experiment. We can see different particles have different optical activity. It seems that optical change might result from the formation and ratio of bidentate and monodentate. Last is our conclusion and future research. At first, we confirmed the precipitate by a clear Tyndall effect. Then, we made a polarimeter which is usable and stable. Next, we discovered that the change of optical rotation suggests the instability of ratio of D-foam and L-foam tartrate in the solution. Finally, in the future, we wanted to do a more experiment to prove our result, and we hope to understand the mechanism. We think it would be a good approach for the initial separation. Thank you for your listening and hope you enjoy our performance. ありがとうございます。
ありがとうございます。それではせっかくの機会ですので、ご質問ありましたらぜひ挙手をお願いいたします。はい、ではマイクをお持ちいたします。お待ちください。
Thank you for a nice talk. I think it's very interesting and a little weird for me, such a kind of phenomena. And because my understanding of your talk is that either one enantiomer preferentially form the precipitate which induce the amplification. That is why it shows the optical rotation. So, if you repeat it many times, eventually you can get the opposite result. But have you ever observed such a kind of phenomena before? Could you show me the slide, the optical study during the precipitation process?
No, we didn't see any report talking about that. So it's
You always observe the result which shows the minus optical rotation even when you change the concentration, right? So which means that always one same enantiomer or preferentially form the precipitate. I'm wondering why either one of the enantiomer is preferentially formed. Can you understand my question?
Can you speak slower? Yeah, I hardly to catch the name.
Okay.
Are you talking about the precipitate? Before the precipitate, you have it's optical active, right?
Anyway, you can get the same result even you repeated the same reaction. You always get the same result? Okay. So another question is, you observe the different optical rotation by changing the pH, right?
Yeah.
And have you ever tried to filtrate when the start to precipitate the form start to precipitate? I mean, if you stop the reaction at 5 to 6 minutes, you can get each enantiomer just changing pH. Have you ever filtrate around 5 or 7 minutes later?
We observe the optical rotation values every minute and records. Yeah, we
record the volume every 30 seconds at the beginning. But we think it's too close, so we change it to 1 minute.
Okay,
Yeah.
after 6 minutes,
Yeah.
have you ever filtrate to get the precipitate at the 6 minutes? So you can get both enantiomer by changing the pH, right? So it's very interesting result, I think.
Yeah, we know our experiment is not it's the particle can form and precipitate. Yeah, it's not a stop. It keep moving.
Okay.
Yeah, so it's
So
hard.
you should try that. I mean, you
Yeah.
have to try to stop the reaction and filtrate.
Yeah. We never try it because Yeah, we can't stop the experiment.
Yes.
It keeps moving. It's
I mean-
hard to choose a time to stop it and get a precipitation. Yeah,
Okay,
it's the
thank you.
question.
よろしいでしょうか。はい、ありがとうございます。それではお時間となりましたので以上とさせていただきたいと思います。ホー・インワンさん、リ・イェンシュワンさん、お二方でした。どうもありがとうございました。